to thank Mark for inviting me to talk. So I will give a completely, I guess, elementary talk. So it's supposed to be for a large audience. So. Okay, so let's start with the objects. So ball quotients. So before taking quotients, you need the ball. So when I say ball quotients, this will be complex ball quotients. So you fix an integer, and you fix the following Hermitian form in n+1 variable, signature n1, on Cn plus 1. Okay, and then the ball is just the usual ball in Cn, which is a set of points in the projective space such that this Hermitian form is negative. So this is contained in the affine chart of Pn corresponding to Zn non-zero. This is an open set, so the usual open ball there inside Pnc. So this is a ball, a complex ball. So there are a few facts about this. First, let us define the following group, PUN1, which is the automorphism group up to scalar of this Hermitian form. So this is a set of elements in PGLNC, which is a set of linear automorphisms of PNC, such that the ball is preserved. Okay. So this is a real algebraic group, and the fact is that so obviously this guy acts on PNC, but the fact, which is kind of classical, is that this action is transitive. Okay, so this ball will be a homogeneous space under this group, and well, the stabilizer for this action is the classical unitary group. And so, in fact, this ball is a symmetric space. So this is of the form G over K, where G is a real simple Lie group, if you want, and K is maximal compact, so this is a symmetric space. Okay. So now, what are ball quotients? Well, ball quotients so for me, a ball quotient will be the following. You fix gamma inside PUN1, what is called a lattice. So this means that this is a discrete subgroup inside PUN1, and moreover that the volume of PUN1 over gamma is finite, where the volume is for the R measure on PUN1, and then the ball quotient will be x gamma. As I said, this is just the quotient of BNC modulo gamma. So because this group is discrete, it will act properly discontinuously. So we can take this quotient. This is topological space. And the first remark is that this is a group of biomorphism. So the complex structure on BNC will descend on x gamma. So usually this will be a complex. Well, gamma can have fixed points, so it's a complex orbifold. But if gamma. So a basic fact about linear groups is that you can always take a finite index subgroup which is torsion-free, in which case the quotient is smooth, and so you get a complex manifold. Okay, so these are the objects. So the first thing I have to convince you about is that such things do exist. Okay, because I'm saying just take a lattice, but why do lattices exist? And so the first, so about the existence. So this is a classical result in group theory, which is due to Borel and Harish-Chandra, is that there is always a way, an arithmetic way of constructing such things. Namely, this is the following result. Suppose that G is R simple algebraic group, like PUN1, then fix a Q form GQ of G. In other words, choose an algebraic variety of a Q such that the R form associated to this is this group. And then if you take the set of Z points, then G of Z inside G of R is a lattice. So the typical example you have to have in mind is, suppose you want to construct an SLNR, G is SLNR, and you want to construct a lattice, then the obvious choice is to take SLNZ. This will be a lattice, and this works for any real simple group. Okay, so these are the objects, they exist, and why should we care? So one reason one could care, and this is the way, of course there are many ways to present those things, but I had to choose one. So why should we care? Well, historically, I guess we care because of uniformization. So let's talk about that. So this is complex geometry. So we care about Borel quotients just because in dimension 1, complex dimension 1, then they are ubiquitous. So why is it so? Well, this is because of the classical Poincaré theorem. Well, I should say Kerber Poincaré. So this is 1907. That tells you that if you are interested in complex manifold of dimension 1, then the only simply connected ones, so the only one connected Riemann surfaces are, well, you have only three possible choices, P1C, C, and the Borel. Okay, and as a corollary, you get that if you stack, if C corollary, if C is a compact Riemann surface, then most of the time its universal cover is the Borel, so it will be a Borel quotient. Well, here I suppose it is connected, then if G is equal to 0, it's genus, then C is P1C. If G is equal to 1, then C is a quotient of its universal cover C by a lattice, lambda, which is Z2. And if G is equal to 2, then C is a Borel quotient. So most of complex geometry in dimension 1 is concerned with Borel quotient. And so you could think that it could generalize in higher dimension. Of course, one remarkable point here is that this group is very simple to describe. This is just a surface group. So you know it by generator and relations. So this is given by 2G generators. And there is only one relation. So the product of AI BI is equal to 1. So those groups are very easy to describe. And so we can ask what happens in higher dimension, and then the situation is much worse. So, sorry? Sorry. Thank you. So the question is, what happens? What are the possible universal covers of compact complex manifolds? Compact complex manifold in dimension larger or equal to 2. I think it was originally probably the idea that all of them should be very simple, like in the case of dimension 1. So this is called uniformization because you know the geometry. And of course, this is completely wrong. But so some remarks about that is that the uniformization theorem. Sorry? No. Here, no. Up to now, not. But I will come back to that. So the uniformization theorem is completely wrong in higher dimension. in the sense that, what do I mean by this? I mean that if you look at connected, simply connected complex manifold, then you have a lot of them. And the easiest thing is to take the ball itself and then try to deform it. Okay? Then if you try to deform it topologically, I mean, you can get then the result is that, how to say that? You get an uncountable family of homeomorphic, not biomorphic domains omega in Cn, or n larger than 2, right? So this is not possible in dimension 1. Each time you will deform the ball, then you will get something which is biomorphic to the ball. But here, this is not the case. Of course, this does not answer the question, because here I'm not requiring that omega admits a compact quotient. So adding the condition that there exists a compact omega over gamma, well, still you have many. And I think Poincaré was also the first to realize the following, that if you take the 2 ball, then this is not biomorphic to the product of 2 1 ball. Okay? And nevertheless, both of them admit compact quotients. Okay? And you have many more other domains, like you have also other bounded symmetric domains. In C to the n. So you have many, many possible domains with compact quotients. And even with all those nice symmetric domains, you have much worse possibilities. Namely, let's look at the following example. Let's say Codera surfaces. So what are those? Well, Codera surfaces are just smooth family of curves. So the Codera surface is just a surface S. So this is a smooth projective surface with a smooth vibration of a curve. Let's say, let's call it C. With fibers of genus G larger than 2. And then you can prove, so this is, by the way, a result of Griffiths, that the universal cover of such a thing is a bounded domain, can be realized as a bounded domain in C2. It's not completely obvious, but it's true. And this domain will almost never be the ball, or one of these bounded symmetric guys. So in fact, even if you restrict yourself to the following question, classify omega bounded domain in some Cn such that there exists omega over gamma compact. This question is completely open. Okay. Nevertheless, I want to mention a few theorems that tells you that those omega really have a bad shape. And this is the following result of Ben-Wong, classical result in complex geometry. Is that as soon as you assume that omega, for example, has a smooth boundary, then you get only the ball. Okay, so suppose suppose you have a bounded domain in C to the n, And suppose that there exists a compact quotient, omega over gamma, by holomorphism. And suppose the following thing, very weak assumption. Suppose there exists a point in the boundary of omega at which the boundary is C2 and strongly pseudo-convex. So this means the following. So the words are frightening, but it's obvious geometry. This means the following. So you have your bounded domain, you assume you are C2, and there is some, so this is kind of smooth, right? You have this point Q, omega is here. You have some convexity in the complex geometric sense. This means that this boundary is locally defined around Q by a function rho. This function is C2, and the assumption that the boundary is pseudo-convex means that the following 1-1 form is positive. This is the natural sense of convexity in complex geometry. So it's a very weak assumption in some sense. Right? I'm just assuming this. And the result of Wong and Rose says that omega is a bon. Okay. So you can imagine that those guys have a very bad boundary. And the dynamic of gamma near the boundary of omega will be very complicated. Let me mention another nice theorem. Question? Oops. Let me mention another theorem in the same spirit. Maybe I can write it here, which is the following. This is due to Frankel in 84. So same assumption, same omega and omega over gamma. But now the assumption is usual convexity. So suppose that omega is Euclidean convex. In Cn. And then the answer is that you are also in a classical case, more general than the ball, but nevertheless in the sense that omega is bounded symmetric. So this result tells you that basically, I mean, of course you have the classical cases, but as soon as you leave those classical cases, then omega will be very complicated. Okay.
What excludes the other convex?
Sorry? So in dimension 2, you have only B1 times B1. And otherwise, you have all Ziegler spaces. And I can give you this classification, but it's not really useful, associated to all the simple group of Hermitian type.
No, but in that convex.
Yes?
The other domain.
Yeah, they are not strictly strongly convex. You have larger or equal to 0. You have some flats.
But there are exotic bounded domains.
There are some exotic, in which sense? Yes, there are some exotic constructed by Piatowski-Shapiro. But some of them have compact quotient, but those ones are not pseudo-convex. Okay. So this is all what I wanted to say for the complex geometry. Let's go to the metric geometry. The fact is that all those ball quotients are not only complex manifolds, they are also Kähler. So ball quotients have a canonical metric. Canonical Kähler metric. Namely the Bergman metric. So maybe I should recall rapidly what the Bergman metric is. So it was constructed by Bergman in full generality in the 20s. It's a very nice construction. It's completely similar to the canonical embedding. If you have a complex algebraic variety with an ample canonical bundle, namely you start with X, an n-dimensional complex manifold. Yeah, I should say that this metric is really nice because it depends only on the complex structure. So in some sense, it's just a way of looking at the complex structure. And then what you do is that you take Hilbert space, separable Hilbert space of L2 holomorphic n forms. And this. So this means that you have an n form, and moreover, when you take the wedge, so this is holomorphic, so this is type n0. When you take the wedge with the 0n conjugate, then you can integrate this 2n form, and you ask that this integration is feasible. Okay, so now what can you do with this Hilbert space? Well, you try to embed X inside this Hilbert space, or more precisely inside the projectivized. So the assumption will be, suppose you have enough such functions, such forms, holomorphic L2 forms. Okay, so basically you assume that for any x, z in x, there exists an n form in H which does not vanish at the point. This is the first assumption. Like in usual algebraic geometries, and what you can do is you can construct a map from X to the projectivized space of this dual Hilbert space, just to map. So you take a point z in X, and you define the point phi of z, and you define it by given its scalar product with any n form in H. And you say that this is f star of z, where you take a local trivialization and you write this form in local coordinates in this way. So of course, this expression depends on the choice of local coordinates, but not the projectivization. If you change the local coordinates, then this, you divide by a constant factor. So this really defines such a map. So now you want this map to be an embedding. And so suppose, moreover, that you have the following condition. Not only you separate points by such n form, but you separate also points and vectors. So this means that for any x in the tangent space at any point tzm, then there exists a form in H, so that f of z is equal to 0, and the Lie derivative is non-zero. Then it's easy to see that this map is an embedding. So why all this? Well, now on any projective space, finite dimensional or infinite dimensional, you have the standard metric coming from the metric of this Hilbert space. So you put it back to X, it gives you a canonical metric, and this is a Bergman metric. So here you have omega pH star. You put it back, you get the Bergman metric on X this way. Okay, so I just wanted to emphasize that this is a completely canonical construction, usually hidden in many, many computations, but the geometric spirit is very simple. And on B and C, you can do that, and obviously it will satisfy A1 and A2, like any bounded domains. And you can make an explicit computation, and you see that this Bergman metric that I denote now by omega is given by this explicit formula, which is very simple. So a point in the ball is a vector z whose norms is smaller than 1. So you take the determinant, you take the log, and you take the del bar of this. And this metric, because it depends only on the complex structure, and the complex structure is invariant under PUN1, this is PUN1 invariant. You can also check it by hand. So this is completely general, but now what are the special properties depending on the ball? Well, first, this is you can check this is scalar Einstein. The Ricci curvature is proportional to the Ricci form is proportional to omega. It has negative sectional curvature, but variable, negative variable sectional curvature. It has constant holomorphic sectional curvature. Sectional curvature -1. Okay, so this metric, because it is PUN1 invariant, it descends to my quotient x gamma, because this is invariant under gamma. So now I'm assuming that gamma is torsion free, so that I have a true manifold. I don't want to deal with orbifold here. And so what do you get? Well, you get on this And let's now assume also that gamma is co-compact. So from now on, for simplification, it's not only finite volume, but gamma is co-compact. So this manifold is compact. So you get a compact complex manifold, and it has a negative metric of negative sectional curvature. So in particular, this implies that x gamma, which is Keller-Einstein, so this implies that x gamma is algebraic, is smooth projective. But much more than that, it really tells you that it has ample cotangent bundle. And so in particular, ample canonical bundle. So it is of general type. Yeah, that's what I'm saying. Gamma is co-compact. I said it, but I didn't write it. Gamma is torsion-free. There are no fixed points. Otherwise, you have to deal with orbifalls, and I don't want to do that. OK, so this means that those quotients are much more than just complex manifolds. They are really smooth projective manifolds. At that point, I guess I should mention the following conjecture related to the first problem of uniformization. So there is a folkloric conjecture. As far as I know, it's still completely open. So suppose you have X Keller manifold of negative Riemannian sectional curvature, so of negative sectional curvature. Then X tilde is biholomorphic to a bounded symmetric, a bounded domain. There should be plenty of those ones, and essentially we don't know how to construct them except taking Ball quotients and some version of Ball quotients constructed by Hsu and Diderot. But still, I mean, it's a big mystery.
The sectional curvature is just the real one?
Yeah, the real one. Real. OK. So what can you do with this metric? Well, essentially, you can compute many things. So using this metric, you can prove many results. The first one is probably due to Calabi and Vesentini, the 60s, and there's also some work of Borel. And it tells you the following, that for n larger than 2, and assuming, I'm still assuming now, from now on, always this. Okay, so X gamma is compact. Then you can prove that using harmonic Dolbeault theory that this is 0, where Tx is tangent bundle. So this means that X is rigid as a complex manifold. And in particular, it means that as a projective manifold, X gamma is defined over Q bar. So not only, I mean, you started with the ball, but now you have some nice variety defined over Q bar. So this means those things tell you that not only the project of complex uniformization by Ball quotients was wrong, but it's completely crazy. You have very few of them, right? I mean, they are completely sparse. They are rigid, so they are isolated in the moduli space, in the moduli space of complex manifolds, but they have nice properties. They are defined over Q bar. So this is the first thing you can claim about them. And the second thing tells you that it's even worse in some sense, or better, depending on your point of view. So this is the result of Hsu in 78. That tells you that not only they are rigid, but they are uniquely determined by their homotopy types. So if you have X compact Keller inside the class of compact Keller, if you have X compact Keller and homotopic to some Ball quotient X gamma, then X is biholomorphic to X gamma. So this result tells you that really everything, all the information you can imagine about X gamma is entirely given by the pi 1. Okay. All right. So all these results tell you that they are some kind of exceptional. So now how can you recognize them? And this is a big question, because It's not obvious. I give you a compact Kähler manifold. Can you recognize that? Then the theorem, which is in fact the only useful one for recognizing a Ball quotient if you didn't start from 1, is the following result of Bogomolov, Miyaoka-Yao. Let's do the following. So this is in just 1 year before Seuss result. Take X smooth. Let's assume now that it's smooth projective with ample canonical class. Okay. Then the result is that you have always an inequality of Chern numbers in the following way. You take the first Chern class, you take its power n minus 2 times, and take the product with C2s, and this is smaller than, larger than minus 1 to the n, n over 2n plus 1, C1 to the n. So this is the first part of the result. And the second part is that equality holds if and only if X is equal to a Ball quotient. So in some sense, if you start from if you know that you start from a smooth projective variety with ample canonical class, it's enough to compute this. If you have equalities, then you know that you are a Ball quotient. And in some sense, it's kind of strange, but this is the only practical criterion to recognize a Ball quotient. So, of course, in dimension 2, you recognize the classical result that C1 square is smaller than 3C2, and you have equality if only if you have a Ball quotient. But this is true in any dimension. Okay, so now I arrive at what I'm really interested in. After this presentation of the beasts, all this tells you that everything, all the information about those things is contained in the fundamental group. So let's talk about the fundamental group. So the pi 1 is just gamma, so we want to understand this group. No, here, no, really you have to be more careful with orbifolds. In fact, I was planning to do that, but in some sense, still you can come back to the first question and answer and say that any compact complex manifold is given by a Ball quotient. In the spirit of Gromov, if you allow orbifolds and degeneration and a lot of things, so there is an incredible conjecture by Gromov that tells you that in fact any variety should be in some sense a Ball quotient. But I really don't have time to talk about that. Well, let me see, what did I write? Yeah, that's you check the constants, that's nice. Is that better? Okay, that's better. Sorry for that. Thanks. You're perfectly right. Okay, so now, yeah. So we see that everything is reduced to understanding the fundamental group. So I already gave you some construction, and it was an arithmetic construction. So by definition, in general, I would say that if I have a R-simple algebraic group and linear and a lattice in set of R points, then I would say it is arithmetic if the following condition is true: if there exists an algebraic group H of a Q and a surjection of H of R, so which is also simple, H of R to surjects to G of R with compact kernel, and such that gamma is commensurable. So this is a mild generalization of what I introduced at the beginning. I'm asking that gamma is commensurable with, let's call P this projection, is P of H of Z. So essentially, this is a set of Z points of some Q structure on G, except that I allow to have more points if these are compacts. Okay. So I already gave you this theorem of Borel and Harish-Chandra, saying that such arithmetic lattices always do exist in real simple algebraic groups. But the question is, can we construct other ones? Okay. Can we construct non-arithmetic ones? If not, in some sense, you have a complete classification, right? Because this is a completely algebraic procedure. You fix a form, namely a Q group, which has this property, and then you just take a set of Z points, and you have only countably many such things, and it's completely algebraic procedure. So it's nice. You're in some sense a classification. So of course, if you are in dimension 1, which is the same thing as PSL2R, we know that there are many others, right? Because arithmetic lattices are countable. But on the other hand, we said that any Riemann surface of higher genus can be uniformized by the ball. So this means, and on the other hand, you have a C3G-3 parameter space of complex structures on a Riemann surface of genus G. So obviously, you do not have enough groups. But already in the 60s, it was more or less clear that this was an exception due to the following result of Weil. That tells you that if you take, as above, so G is simple, real algebraic group, and you take a lattice in G of R, and then if G is different from PU11, then gamma is locally rigid. In the sense that you cannot deform it. You have this lattice, and you try to deform it inside G of R, take a one-parameter family of deformation, then I claim that it's always conjugate to the original one. So you have only trivial deformation by conjugation. Okay, so it tells you that already this phenomena of having moduli spaces does not exist. And this was reinforced a few years later by Mosto and Prasad for non-compact. In 73, tells you that if you are in the same situation, gamma lattice in G and gamma prime lattice in G prime, and if you assume that gamma is isomorphic to gamma prime, then in fact such an isomorphism extends to under the same assumptions and SL2C. Or PU11, PSL2C. All right. So the first result tells you that you have very few such gammas, and the second tells you that they are highly independent. Maybe if you have two of them are isomorphic, then in fact, I mean, if this extends to an algebraic isomorphism. Around. Okay. So still, you can do better. So you would like to understand the algebraic properties of those guys. For example, their representation theory. At least finite dimensional one. And so the main result in all this area is the following theorem of Margulis. 79 tells you that suppose now that you take a group of rank larger than 1. So in particular, not PUN1. Okay? And suppose that you take any group of any local field, which is simple, and let's say a joint, for simplicity, algebraic K group, where K is a local field. And suppose you take any representation of gamma, which is a lattice inside G of R, to H of K, and you want this representation to be non-trivial in the sense that this is unbounded. for the topology on h of k deduced from the topology on the field, local field k. Then k is Archimedean, is RC. And basically, this is given by the trivial representation. Namely, you add this morphism here to h of k. Now k is RC, and this extends to a morphism of Lie group and even algebraic if you are in algebraic. And the corollary of this is that if gamma is a lattice in G and rank of G is larger than 1, is that gamma is arithmetic. So in some sense, so this is also due to Margulis, these are two incredible theorems that tells you that if you take a lattice, its representation theory in finite dimension is completely simple. It's given by the representation theory of the ambient group. And as a corollary, you get a very precise description of all those guys. I mean, essentially, they are just a set of z points for a Q structure in your group. So these are really amazing theorems. I want to give a hint about how you deduce arithmeticity from superrigidity. So what is the idea of the proof of this? So you start with your lattice in G of R. And then the first thing you do is you use the fact that gamma is rigid. So if it is rigid, this means that you look at the variety of representation of gamma in G of R. This is an algebraic variety defined over Q. If the guy is rigid, this means that in the moduli space, it represents just 1 point. So this means it is definable over some number field. So this means that up to conjugation, you can assume that gamma is contained in G of k, where k is a number field. And now you use the fact that gamma is finitely generated. It tells you that gamma is in G of OK 1 over n, for some n. So there are only finitely many places that play a role. And now, well, you take V dividing a place of your number field k dividing n, and you look at the induced embedding in G of kV, just by completing your field as a place V. So what did you see? Well, now you apply Margulis superrigidity, and it tells you that, so superrigidity tells you that this has to be bounded. And this is true for all places dividing V. So this means that, in fact, gamma is contained in G of OK. Okay? In which case, you say that the lattice is integral. Okay, now to finish the argument, you just look at all the real places. You can assume that K is totally real, and you look at just at all the real places which are not the initial one. And using Margulis superrigidity once more, you prove that those are compact. And so you get an arithmetic lattice there. So that's the idea of the proof. So now, what is the main question? Well, you see that this theorem is fantastic, but it does not apply in rank 1. And this is why also ball quotients are so marvelous. So what are the remaining cases? So in rank 1, well, you have only four types of groups. You have PON1, the same group but for quadratic forms. PUN1, SPN1, and F4 minus 20. So they all correspond to hyperbolic geometry over different fields: reals, complex, quaternions, and octonions. Okay? And then you can ask first for superrigidity. This is the strongest property, as we have seen. It implies arithmeticity. Well, and here everything depends on which side of this line you are. If you're on the right, then the answer is they are still super rigid. Yes, and this is a result due to Corlett in 92 and Gromov and Schoen in 93. So this implies in particular that they are locally rigid and that they are arithmetic. So this implies this, and this implies this. So the answer is yes and yes. Okay, so let's look at what happens for real and complex. So P1, then the answer is no for all n. In other words, for all n, you can exhibit non-arithmetic lattices here. And this is due to Makarov and Winberg in small dimension, and to Gromov, Piatetsky, Shapiro in all dimension. And so, as above, this implies that the answer here is no. There is no direct implication as far as I know for local rigidity, but in fact the answer is no. So here by local rigidity, we have seen that all these lattices are rigid in their ambient group. But what you can do is, so for local rigidity, I mean the following now, is that you take the ambient group G, so you have gamma in G, and you fix an algebraic representation in some other group, G prime. And then the natural question is, can you deform gamma in G prime? You know that by Veil rigidity you cannot deform it here, but it might be possible to deform it in a bigger group. And if it is not possible, we say it's locally rigid. And the answer here is that no, you can deform, in fact, you can deform most lattices in PON1 can be deformed in PON plus 1. This is a result essentially due to Johnson and Milson. Okay, and now you understand what the point of Ball quotients is. Those questions. Okay, so what is known? I'm very late. Okay, so there are a few results concerning arithmeticity. First, they prove in the 80s that there exist non-arithmetic lattices, but only in small dimension. In SU21, PU21, and PU31. This is completely open in higher dimension. Finitely many common subarability classes, yes. At least up to now, we know only finitely many. So because there exist non-arithmetic lattices, this means also that there exist non-superrigid morphisms. And but the situation is even worse than that in the sense that most prove in 80s the following, that there is the following terrible situation that can occur. You can have an arithmetic lattice gamma subjecting onto another arithmetic lattice gamma prime with infinite kernel. And those two guys are arithmetic. So this is typically bad, because this means obviously you cannot extend such a thing to a morphism of algebraic groups, right? Because you will never have an infinite kernel. So this is really the worst possible situation. Sorry? So it is in PU21. Yeah. So in front of that, what are the questions that you can ask? Well, you can play many different games. But the main idea of the game will be that Kähler geometry for the quotients of the Ball quotients, complex Ball quotient, should help a lot to show that those guys are much more rigid than in the real situation. So let me try to explain a few games you can play. So game one, try to exhibit rigidity properties for all lattices in PUN1. So I played this game for many years. I never succeeded. But nevertheless, I have a conjecture. I'm quite confident in it. This is the following conjecture. Basically, it tells you that all the problems come from the real places. In other words, suppose you have a lattice in PUN1, which is co-compact. Then I claim that if you take any row, you have to get rid of this problem. So the way to get rid of is to look only at faithful representations. then any row from gamma faithful into G of QP, where G is as above some simple p-adic group, has bounded image. If this conjecture is true, the corollary is that gamma is integral in the sense that I described here. It's always contained in the ring of integers of the group, but there could be problems for arithmeticity coming from the infinite place. Okay, I don't want to say any. I have nothing more to say about this conjecture, except I believe it is true, and I hope to prove it one day. So game 2 is another game. Is try to prove arithmeticity under additional condition, additional geometric condition on the quotient. And here the main idea is the following. If this manifold has many properties similar to higher rank quotients, then maybe the lattice is also arithmetic as it is in higher dimension. And what happens in higher rank? Let me give you a flavor of this game. In higher rank, if you take a lattice in a Hermitian group of higher rank, then its first Betty number is always 0. It has property T of Kashdan. And B2 of gamma is 1. Just the Keller class, nothing more. So the Picard Néron-Sevry group is Q. So the conjecture, which was done by Rogawski for surfaces, but I hope it works in full generality, is that suppose that X gamma has Néron-Sevry group of a Q, which is equal to Q. So same conditions as in higher rank. Then gamma is arithmetic. So once more, I did not succeed proving this in full generality, but let me give one case where I succeeded and which proved to be of interest for algebraic geometry is the following case. So example was the following theorem that I proved in 2003, a long time ago. Suppose that X, first you are in dimension 2, and second, you have a much stronger condition than this. Not only you assume this, but you assume that this is a fake CP2. So same Betty numbers, not only this, but same Betty numbers as P2. Then gamma is arithmetic. Okay, and with this theorem, this led to a complete classification of fake CP2. Because once you know the lattice is arithmetic, there are methods from number theory to try to compute what are the possible gammas such that the quotient has the same Betty numbers as P2. And there was a complete classification by Prasad, Young, Cartwright, and Steger, and the answer is that there are exactly 100 fake CP2s. And this is just the beginning of the stories because this surface have many interesting algebraic properties. For example, they are my favorite candidates for testing the block conjecture on surfaces that we talk a lot in the algebraic geometry seminar. Okay, I don't want to say more about this one. What I want to talk about now is the following game. Game 3. Better understand arithmetic lattices. And here things become more subtle in some sense. So I will just recall you the structure of arithmetic lattices, and more precisely even congruence lattices. So I recall you the structure of arithmetic lattices. How do you define a Q group such that you get a SUP1 on the real points? Well, you fix a totally real number field take a CM extension. You take a division algebra of a FC of degree d dividing n plus 1, because you want to construct a group of the form SUN1. So I will write n plus 1 as being dr, d times r. You fix Hermitian form, and the way to do it is first to fix a involution of second kind on D, and then you fix H an epsilon Hermitian form on D to the R. And with all this arithmetical data, you get canonically a group of Hermitian type, a form of SUPQ, just taking, so we get a group of F, which is by definition the special unitary group of this form H. And you want this group to have row points which are SUN1 times compact. So the hypotheses that you make are the following: that for one real place V0 of F of this totally real number field, your group is SUN1. And for all real place different from V0, then your group is SUN plus 1. Now, what is an arithmetic lattice? So an arithmetic lattice defined by this Q group is any gamma commensurable to G of OF. And now inside those ones you have the congruent subgroup, which are the guys of the form G of F intersected with compact open subgroup G of AF. So it's still not known. This is another problem I don't have time to talk about. But the congruent subgroup problem is not known for many forms of SUN1. So it's not clear that any arithmetic group is a congruent group. When it is, when you work with congruent lattice, ball quotients are called connected Shimura varieties associated to the ball. So now what is the picture? The picture is the following. The main parameter in this story for constructing the group is this invariant D, the degree of the division algebra you take. So if D is equal to 1, in which case your algebra is just a matrix algebra, this is kind of easy to deal with. In some sense, this is more classical. And I will call the corresponding lattices cache-down lattices. If D is equal to n plus 1, then I would call them, following Laurent terminology, Kotvitz lattices. And otherwise, D is somewhere and adds to divides n plus 1. I don't give any name. But the idea is that the topology of X gamma and the geometry of X gamma will completely depend on this D. So for example, cache-down proved here that the virtual first Betti number of gamma is positive. Namely, you can always find a finite index subgroup such that the B1 is positive. On the other hand, there is this remarkable theorem telling you that whatever the finite index subgroup you take, it does not change anything here. The first Betti number stays 0 inside congruence lattices. Yeah, so here I'm taking only congruence. And this is due to Rappaport and Sink in dimension 2, and to Laurent in general. Okay. So you can try to so in some sense it tells you that here there is some kind of abelian rigidity. There are no abelian representation of gamma. I mean infinite with infinite image. So we can try to generalize this, and yeah. So the theorem that I want to mention, I did recently, was a generalization. Here it tells you that there are no holomorphic one forms. Okay, then you can ask for more. So take a Kotvitz lattice and assume I make a strong assumption that n plus 1 is prime. So I don't want to have divisors. Then I improve this kind of result by proving any row from gamma to GLN minus 1C is rigid. In other words, the variety of representation from gamma to gln minus 1c, and take the quotient by conjugation, is a collection of points. Finite set of points. And B, any row from gamma to gln minus 1 c, sorry, F, where F is non-Archimedean, let's say QP, as bounded image. So I cannot prove super rigidity, but I can prove some kind of very strong rigidity, but not in the right range. For arithmeticity, I would need n plus 1. I cannot prove it for n plus 1, neither for n, but only n minus 1. So I do not recover arithmeticity this way as a bounded image. May I take 2 more minutes? Yeah, okay. So I will try to give just a fast idea of the proof of this. So what's the idea of the proof? The idea of the proof is to use both algebraic geometry and number theory. So algebraic geometry will be non-abelian Hodge theory. So proof. And this is a following theorem, which is due to Hitchin, Simpson, Arapura, Kaczarkov-Zuo, and maybe myself, but I'm not sure. You want to control representations. And the idea is that on algebraic varieties, most projective varieties, you can control them if you control symmetric differentials. So X-connected compact killer, and gamma is pi 1 of x. Suppose that you don't have symmetric differentials in degree smaller than r, then you then any row from gamma to GL RC is rigid. And so exactly the same conclusion as there. Any row from gamma to GL RQP is bounded. So this is really non-abelian Hodge theory. For those who are interested, I can explain the proof in a few words just after, but as I'm already late, I will not say that. So this is the algebraic geometry part, complex algebraic geometry part. Okay, so now you have to prove this vanishing theorem. And here, this is really arithmetic. This is automorphic formed. So, theorem 2 will imply this theorem 1. So what is theorem 2? Theorem 2 tells you that if gamma is Ball quotient, I mean, it's Kotvitz lattice, and n plus 1 is prime, then this implies this vanishing. So you see, this vanishing is really kind of strange. We know that it really depends on the type of the lattice, because if gamma is Kashdan, for example, not given by a divisional algebra, but by a matrix algebra, this is false already for I is equal to 1. Okay, you have holomorphic 1 forms. So this really depends on this. And this is also surprising from the point of view of geometry, because I told you that those Ball quotients, their cotangent bundle is ample. So this means that for large I, SI omega 1x is generated by global sections. But the question is, what is the first n where you begin to have sections? Even if those guys are generated by their sections for large I, it happens that up to n minus 1, you don't have sections at all, right? Which is quite common in algebraic geometry, but it's still pleasant to see it in such a case. So I don't want to explain the proof of this. I mean, this is really automorphic forms following the work essentially of Laurent in that case. And okay, so I will just stop here.
Thank you very much.